Hello, everyone. My name is Shasta,
Hi everyone, I'm Vishal.
and we are the team for Project Midnight, which worked on domain adaptive low light raw image enhancement for smartphones. So, currently, what are the challenges that exist in extreme low light imaging? For starters, since low light images have short exposure times, there's low illumination and increased noise. And additionally, since we're focusing our project on smartphone cameras, we experience further degradation compared to DSLR cameras due to their lower quality. And as you can see in these images here, we got a low exposure image trained up towards a higher quality image towards the end. Different cameras also yield different color mapping. So as you can see here, these three images of the same exact photo shot or the frame yield slightly different colors due to the fact that they're across three different cameras. So how does our project address these issues? For starters, we are using our own smaller data set. We implement our own unique deep learning model architecture, and we investigate the hypothesis of raw to sRGB image enhancement and denoising performance using various metrics such as PSNR and SSIM to measure their effectiveness. And lastly, we're comparing with previous state of the art. So for capturing the data set, we went around campus, captured 180 different shots. Here's some of the frames from the OnePlus, iPhone 11, and Google Pixel smartphones we used. The black image on the left is the short exposure image, and the colored image on the right is the ground truth image we used to train up to it. And comparing our data set with other data sets simply just highlights the fact that our data set consists of smartphone images, and we are actually using the same scene, which was not always used in the past.
This is the previous state-of-the-art work, learning to see in the dark. The input is a Bayer raw pattern, which is then demosaic to get 4-channel input. Then we multiply this by the amplification ratio, subtract the black level, and pass it through the convolution neural network to obtain a 12-channel output, which is then subject to a pixel shuffle operation to obtain the output RGB. Our proposed method builds on top of this to include a source-specific encoder and a target-specific encoder, a shared network. And then as you can see, the red arrows show you how the DSLR camera raw image is passed on through the network through a 16 to 8-bit converter to get the source loss. And the blue arrows show how our smartphone camera dataset, which is the target domain, is utilized. In this work, the source dataset enhances or enables us to work with a smaller target dataset. So these were our results at the MVP presentation. So this was a good learning experience because we learned that our input dataset did not have much illumination at all. And so it was a very constrained or hard problem to solve compared to the dataset from the previous state-of-the-art works.
We threw together a quick video to summarize the Project Midnight process. First, we did a literature survey, deep dived into the field of low-light image enhancement. Next, we had to capture our data. And voila, here's the long exposure image. Here's me implementing some code for our MVP in the VR lab. And here Vishal is running a training on a Nautilus pod in the computer vision lab, and you can see some of our model's output results here.
Here are our qualitative results for our raw-to-raw experiment with the Google Pixel camera dataset. So here on the left, you could see the input images that are passed on to our deep learning network, and the output. After 800 epochs, it's quite good, but it has a lot of image artifacts, especially farther from the scene, which is out of focus. However, as you can see, when our model converges at 2,500 epochs, the results are much better and it's able to preserve a lot of scene information, both for outdoor as well as indoor scenes on the right. Here we compare with LSID, the previous state-of-the-art that we spoke about, and we show our results to be much better for smartphone cameras, much closer to the ground truth in terms of PSNR and SSIM. Lastly, we also show denoising performance, and we show that the overexposure in some of the images is mitigated by our method, and it's much closer to the ground truth in terms of SSIM.
And our next steps are to continue finishing our analysis for our final qualitative and quantitative results after our model converged. We want to further compare our results with previous state-of-the-art baselines And ultimately, we're doing all this to submit our official research paper to the ICCV workshop on resource-efficient deep learning for computer vision.